Please stand by.
Do I look good, you guys? Do I look camera-worthy?
Good.
Liars. Chris or Terry, would you mind bringing back the attendance sheet? Okay, and the DVD? Thank you.
Live.
Good afternoon and welcome to Purdue University, the CERIAS Security Seminar. Our speaker today is Professor Xiangyu Zhang, who is a CERIAS affiliated faculty member from computer science here at Purdue. Xiangyu.
Thank you for the introduction, Joe. Good afternoon, everyone. Today I'm going to talk about program analysis in security. This is pretty much some of our work, and some of the work actually belong to a student sitting in the audience. Today I'm going to cover three topics: binary transformation, memory forensics, and reverse engineering. All these three applications, I would say, they're all driven by program analysis. So what's a program analysis? Program analysis is to analyze your code or your program execution to identify problems, for example, security vulnerabilities in your program and things like that. So these three topics, let me give you a little bit of a brief introduction. Binary transformation, what does it do? So for example, you give me your Windows Word. I'm going to insert some code into your Windows Word, or I'm going to extract some code from Windows Word, right? So to make it do something slightly different. Right? This code could be malicious, could be benign, but it just adds some additional semantics into your program, right? So in other words, I transform your program to do something slightly different. So what is memory forensics? Memory forensics basically is that, it's like just forensic techniques, right? So this time, instead of looking at something on your hard disk, we're looking at your memory image. We take a snapshot of your memory, then we try to identify important information from memory snapshots. For example, your password, your contact list. This will be very helpful for law enforcement. Right? So the third one, reverse engineering. What does it do? Basically, what we're saying is that, for example, you download a piece of code from internet, and then you're not sure this piece of code is doing something that is claimed that's doing, right? Then we actually analyze this software, try to reverse engineer the hidden behavior of the application and expose all this hidden behavior to you, right? So I will try to make it informal, and we're going to skip a lot of technical details. I give you the basic ideas and show you some demos. Right? If you are interested in the technical details, please just raise your hand, and then I'm happy to answer questions, right? So the first one, binary transformation. So binary transformation has a lot of applications. For example, you can use it to debug. You can use it to provide performance of your programs. For example, my app is running very slow, or it's taking a lot of energy. What's going on there? So usually, what people do is they're gonna insert a small piece of code into your program, try to monitor the execution of the program, right? Then we give you some profile result, and then from there you can understand what's problem with your code. If you ever use things like for gprof, jprof, those are the probably most popular profiling tool. So those two actually will transform your application, right, to collect such data. And what we're doing here is that essentially we transform your binary executable without requiring your source code. Right? Of course, you can do security hardening. I guess by now you should know that security hardening is to add a small piece of code into your program so that you can avoid a lot of security problems. Right? So again, you have to transform your program. Now, there have been a lot of program transformation tools. For example, you can do source transformation or source instrumentation if you have your source code, right? You have your compiler. But the problem with those techniques is that they require source code. What if I dynamically load a piece of library code, right? Then you don't have the source code, right? So you cannot transform that code. You cannot instrument the code. Now, of course, then people try to look at binary instrumentation or binary transformation. There, you don't need the source code. But of course, then you have to handle a lot of difficult challenges. For example, how you're gonna handle the register, how you're gonna handle indirect call, indirect jumps, right? So binary actually look completely different from source code. If you ever disassemble a piece of code, right, they will look, all you see just instructions, registers, memory locations. You never have, for loop, while loop, or variable name. You don't even have those information, right? Now, then our goal essentially is to to do the following: try to instrument commodity binary programs or even the kernels, right? So in the presence of all the possible anti-instrumentation schemes. So one thing I want to talk about is that if you try to apply such a binary transformation technique on some binary that are probably malicious, for example, they usually have self-protection scheme, right? They will detect whether this piece of code has been tampered with by anybody, right? If that happens, they're gonna just quit on you, right? So then one of our goals is that we try to do this stealthily, so that even we transform your code, that code cannot detect our presence. So then we talk about two pieces of work. Both of the, all this work I talk about today, they're actually kind of published in top tier conferences. The first one is bistro. Bistro is a technique that allows you to extract a piece of code from your existing binary. For example, you give me your Firefox, compile Firefox or Chrome. You're going to extract a functionality out of Chrome, and again, we can port it to another binary. Okay. So the second capability of bistro is that it can insert a piece of code into an existing binary executable, right? And then it works on a large commodity programs. We have tried on Windows Word, Firefox, and we have tried malware. One of the demo I'm going to show to you is that we actually extract components from existing malware, okay, 3 components from existing malware, and then we compose a new malware using those components, okay, so using our tool. Right, that's bistro. And Spider, you can think of as a stealthy version of bistro. So here we actually do it in a stealthy way by using hardware virtualization. Right? So I will give you a little bit of idea about the high-level design of bistro. Then I will go into the case study. Right? So bistro essentially it works like this. Okay, you're given a piece of executable. We're gonna stretch. How are you gonna insert a piece of code into a existing executable? Think of that, right? So if you simply just if you ever play with, for example, advanced editor like Ultra Editor, right? You try to open your binary code and then you insert instruction into the binary. See what happens. It's gonna crash on you, right? It's gonna break. Okay. So what we're doing here is that we try to get your binary, then we're going to stretch your binary so that we create holes, and then you can insert instruction into those holes. Right? How do we stretch your binary to create holes? For example, in binary you usually have this jump instruction, right? For example, JMP5, jump 5. What does it mean? So can anyone tell me what does it mean? Jump to the offset 5, right? So if I want to insert instruction, right after that jump instruction, what should I do? I change the jump 5 to jump 6, right? Okay, that's the basic idea. Of course, there are a lot of more challenging cases. What if the jump instruction has a dynamic computed address? What if it's a jump EAX, right? Then you have to do more than that. Okay, but of course that's related to our design, which I think I will skip. So this diagram actually kind of illustrates how our things work. Right? So on the top, you see the binary one. It's a first executable we provide to the system, and binary 2 is another executable provided to our system. Then what we want to see here is that we want to extract the brown component from binary 1 and the blue components from binary 2. And then we have 3 components. And then we want to insert these 3 components into another existing binary, it's a target binary. Right. The way that we do it is that we're going to stretch that existing binary, which is the yellow one. Okay, we create those holes, and then we insert the blue components and the brown components into the extracted or stretched binary, so that we get a new binary, and this binary will contain the original yellow semantics and also the inserted semantics from the blue and the brown components. All right. So any questions? So the basic algorithm, gonna skip. So we handle indirect calls. Like I said, we have a jump EAX, those kind of instructions. We are able to handle them. if you have callback function is another problem because, for example, you usually the callback function works like this. You provide address to the library, right? In the library, we use that PC address, the instruction address. We call back your user function. Now the problem is that, but we already stretch your user code, then your user function entry now become offset, right? Then you have to fix the offset. Otherwise, when the library make the callback invocation, they're gonna call it wrong place, and then you're gonna get a crash. Okay. So we handle all that. So basically, and then another problem is that you need to handle the data references. What does it mean? Because when you ever disassemble a piece of code, usually you see there's a session called a data session. Okay. What does it do? It actually contain all these global data structures. Okay, this global data structure usually may contain information like your function pointers. You need to fix those function pointers in order to make your technique work. Okay. Then we implement this technique as part of the IDA Pro plugin. If you ever use IDA, I mean, a lot of you, I guess, use IDA to disassemble like binary code, right? We implement our technique as a part of IDA. And then our technique currently support Windows PE binaries. For example, you give us your Windows Word or Windows PowerPoint. We actually can perform a lot of transformation on your code, right, without any source code. And there are some performance data I want to show you. And this is the overhead. You look at the last 3 bars, which are the average overhead of our technique. The red bar actually represents the runtime overhead. You can see that in most cases, on average, we only introduce 2% overhead. This is really attributed to handling the indirect cost. Right? You look at the blue bar, which is the last one. I mean, on your right hand side, that's the file size increase. So we increase your file size by probably 10%. Okay, so if you give us a binary, we actually increase the size because we have to store some meta information for us to work, for our technique to work. Right. So you can see that we have tried a large, a set of Windows large programs, including Acrobat Reader, Chrome. We actually have also tried Firefox, malware, and all that. So later on, I'm going to show you a demo. All right. Extract and reuse binary components. I think this demo is less interesting compared to the second one, which is so-called the malware stitching. All right. So we extract components or extract payloads from existing large malware, and then we compose a new malware from those extracted components. So configure C actually is that's a famous malware. I guess a lot of you have probably have studied it. Right? And then we try to extract 3 components from this malware. And this malware actually contains a lot of different kind of payload. We're only interested in 3 of them. The first one is get PID, which is get a process ID of a given process. The second is inject. Inject essentially is inject the malware itself into an existing process. Okay. The third one is a so-called hook DNS. Essentially, if you hook the DNS lookup function, so that we redirect your DNS lookup to a different, different location. Right. So these 3 functions essentially already exist, in the malware, and now we want to extract those components and we want to build a malware out of these extracted components. And assume that we already extract these 3 components. What we want to do is to implement this logic. Okay, this is a very simple logic. The logic is that we compare whether the current process actually is inside IE. If this is the IE process, then we're going to hook the DNS. That means we're going to intercept the DNS queries inside IE, right? Otherwise, if this is not an IE process, what we would do is that we're going to get the IE PID, and then we're going to inject the malware into the IE process, so that when IE executes, our malicious payload, which is the DNS hijacking, will actually get triggered, right? So this is a very simple logic, right? but we actually make use of the 3 components that we extract to implement this simple malware. And then the goal is to prevent IE to access the Microsoft.com. So like I said, our tool have 2 aspects. One is to extract, the others allow you to insert the components. So this is the executable of configure.c. And then we obtain this sample actually from SRI. If you know, SRI is one of the most famous vendor on malware analysis. And this is the script that allow us to extract the 3 components. And this script essentially will invoke the functionality of bistro, right? Because this is the we open IDA, we then disassemble the malware, and these are the 3 functions that we try to extract. Right, the first one is a hook DNS, you can see. And this one to show that if you want to extract a piece of components, remember that the piece of component actually will access data in your, for example, in your global session, right? So you may access some variables that, that's part of your binary, but it's not in the code, it's in the data session of the code, right? If you know that a piece of binary usually consists multiple sessions, they have data session, they have code session, right? And the data that you access by your code usually, reside in the data session. So when you extract the piece of code, you have to extract the corresponding data entry as well, right? So this graph shows you that we also extract those data entries. Now we execute bistro. Then we got 3 binary components, okay, corresponding to the 3 functionality that we're interested in. They're pretty small compared to the original size of configure. Configure originally is like 172K, and now we only extract component with the 2K, 6K, and 2K, just a small piece of it. Yeah. So next thing is that we try to make use of these 3 components and compose a new malware. Right? Again, we're going to use bistro. We stretch the original binary, insert those 3 components. So the way we do it is that we actually write a small program like this. This program actually corresponds to the 4-line logic that I presented earlier, which is tested whether I'm in IE, otherwise I will inject myself into IE, right? So this is the implementation, but all we do is that we actually provide empty functions for this hook DNS, and then the also get processor ID. Those functions, they are empty right now in our program. Okay, we compile it, we get a piece of code, but the piece of code only contains 3 functions, empty functions for those 3 parts. And then later on, we use bistro to replace those empty functions with the component that we extracted. That's how we compose a new malware. All right. You can see the highlighted places are the 3 function calls. And right now, they're all dummy. Otherwise, they have empty body. Right. Then we're going to replace with our extracted components. And also, we let our malware to pop up some messages to show that it works. Okay. Now we compile our small C code. We get a DLL library. Then we use our bistro tool to insert those components into the compiled DLL. And so now we got a new DLL, which is have the size of 12K. So now we're going to test, we're going to execute our new malware, see what happens. So we first start a clean IE to access Microsoft.com. Everything looks fine, no problem, okay? And then we're going to execute our malware. But our malware, since it's a DLL file, you have to use a debugger to trigger the DLL, all right? So here we are using a immunity debugger. And then by executing this DLL, we inject itself into our IE process. Now this IE it become infected. So now it has been infected. We try to access Microsoft.com. Now this time you can see that. Okay, it's the same process. We're doing a dynamic infection of IE process, and then now we deny your DNS access. All right. Okay. Any questions?
Is there a particular reason for running it on XP, the demo there? Does it work in 7?
That's even easier. We show it on XP because XP is more difficult. Because there you have those binary, you don't have a relocation table. I mean, because at that time, adjust randomization probably is not as popular as nowadays.
Okay.
In Windows 7, because you have the relocation table, Bishop become much easier. So for legacy code, since you don't have a relocation table, handling indirect code and indirect jumps become much difficult. So we are showing the difficult case instead.
Interesting.
Okay. Any other questions? All right. Oopsie. Just stop right here. All right. So, all right. Spider. I will just quickly go through Spider because there was some student waiting to see his own work being presented. And Spider essentially is like I said before, it's a stealthy version of Bistro. Now this time we want to do it a stealthy way, right? We don't want any of your the malware or any of your, for example, if you run a game program, usually they have self-protection, okay? You run the game program on the debugger, they're gonna just shut down on you, right? So in order to kind of intercept the execution of a game program or malware, you have to do it stealthily, okay? Or you add something into the game program, you have to do it stealthy. Then basically what we do is that we leverage hardware virtualization to achieve this goal. And we can instrument your program, including malware, including your game program, which have the self-protection. Now we can hide our presence through virtualization. But we are using hardware virtualization, which is much faster than software. I mean, the other kind of virtualization, right? So this is the basic idea. I'm gonna skip that, and this is the result. Basically, what we are showing here is that with our technique, we are able to, avoid all the existing kind of a protection scheme. So these are the program, the target. The first column shows the target. Essentially, these are the popular self-protection scheme. You can run. If you have a program, you run those programs. They're gonna insert some self-protection mechanism into your code. And then we are able to show that our technique actually can evade all this technique. And of course, our technique has some overhead, but overall it's much faster than the state of art. Right? Right, I will go into the second project, which is memory forensics. Again, all these techniques are driven by program analysis. Analyze your program, analyze your program execution, then to achieve our goal. Right? Memory forensics. So what do we do in memory forensics? This is the image. You have a RAM, and then you have some data, and the data look very ugly. They're all bits and bytes, right? And if you want to understand some information, for example, your password, your contact list from this memory image, it becomes very difficult, right? How do you interpret this piece of memory, right? Okay. But our goal is still, we want to scan this memory image, identify some important information, like your password. Memory forensics, besides the application in forensic analysis, crime scene reconstruction, They can also be used in many other applications. For example, kernel rootkit detection. Right. So kernel rootkit is a malware at the kernel level. So kernel rootkit usually will hide itself. Right. The way that it hides itself is to eliminate its presence in the process task list in your kernel. Right. So when you execute a command like ps, right, what will happen? You go through a linked list in the kernel, which is so-called a task list. Okay, this task list actually will link all the active processes right together, and then when you call the PS, we're going to traverse individual nodes in your linked list, each node representing a live process. Okay, so then let's say the middle one essentially is the rootkit process. The way that it hides itself is that, how about I dislink myself from the linked list? Okay, and now you have a shorter linked list. This time you run PS, we're going to show 2 processes, right? Compared to the previous one, which showed 3 processes. Now, in other words, you won't see a weird process, which is the rootkit process, right? Now, but this node in the middle cannot completely hide itself. It's still in your memory, right? Because otherwise, you don't have the PCB to run the process, okay? So what we would do using memory forensics is that, how about we scan your memory, identify all the task list data structures, and then we're going to expose the one that try to hide itself. Right? So now the key challenge is that, how do we identify important information from those bits and bytes of your memory image? Right? That's the most important challenge. Now the state of art usually does this. To identify some magic numbers in your data structure. For example, let's say your task list, your task data structure usually associated with some magic number. That's the last field in the data structure, right? Identify that magic number. You're going to scan the memory to identify the presence of that magic number. And as long as you see that magic number occurs, then it's an instance of the data structure. Okay. Then you can see what's the problem of such a technique. You can imagine this magic number may not be unique, right? So there's a lot of coincidence that you have other occurrences of the same number in your memory, right? Then you find a lot of false positive. And so our approach actually falls into program analysis, and then we have a line of work actually start from SIGGRAPH, and then we have a second project with Dim Sum, and then we have the Discrete, which just won the Best Student Award. I mean, actually, this is a work by Brendan, sitting right there. It's won the Best Student Paper Award in this year's security. Right, the basic idea is that, let's say you have some data structure, you have some information that you want to extract from the memory, okay? And this information usually corresponds to some data structure definition in your program, right? So look at the task list. The task list actually corresponds, 3 data structure. If you look at the source code of the kernel, usually that's what you see, right? Now, from this data structure declaration, what can we do? We can construct a signature, okay? So this signature look like this. Task S means that if the memory location starting at X, if that is an instance of task, then we can infer the memory location starting at X plus 0 got to be a pointer pointing to a thread data structure, right? That's actually according to the data structure declaration on the left-hand side, right? And then also, if you look at the second piece, which is the offset X plus 4, again, is a pointer pointing to a data structure MM. Okay, this have to be respected. These are the constraints of your data structure, right? Now, what essentially have is that we can, if we see there's a piece of memory locations, if the first word is a pointer pointing to a thread, and the second one is a pointer pointing to MM, the third one is a pointer pointing to signal, from that information, then we can infer with high confidence that the original pointer X gotta be an instance of a task, right? That's the opposite inference, right? Now what we are doing here is that we are building a graphical structure, right? This graphical structure look like this, right? The root node essentially represents a structure of task. With that, it means that the first offset gotta be a thread, and the second offset gotta be an MM, the third offset gotta be a signal, the fourth one gotta be a task. And this one is just one layer of signature. Essentially, the thread, right? The thread. Look at the first field, which is the thread field. The thread itself also has its internal structure, right? We can further expand it to kind of enhance our signature. Look at this. If you want to identify instance of thread, and the first field of the thread data structure gotta be a pointer pointing to a task data structure, right? Again, now we kind of keep expanding our graph, then we have a gradually growing signature of your data structure, right? Now then we call this one is the signature of your critical piece of information. Now we start using this piece of signature to scan your memory image to identify occurrences of those data structures. Right? Let's take a look at the example. So here you can see that on the top essentially is a memory image, and the bottom essentially is a graphical signature. We want to use that graphical signature on the bottom to scan the memory image on the top, right? And right now I want to determine if the underlined memory location is an instance of task or not. Okay. What I would do is that now look at the first offset, which is the first 4 offset, and we try to determine if they are pointers pointing to thread, signal, and task, right? Then I got the reference based on those 4 pointers that we get to the other data structure to see whether this one should correspond to a data structure of thread, and the second one should correspond to a pointer pointing to right? And the third one, when I dereference that pointer, I will go to a location. This location gonna be a instance of signal, right? And the fourth one gotta be a pointer pointing to a task, right? So if all these constraints are satisfied, then we identify an instance of a task, right? Okay. This is basically we use a graph to scan your memory image to identify the instances. Any questions? Of course, this is just a basic idea. There are a number of challenges. What if your multiple data structures share the same graphical signatures? That may happen, right? In this case, we're gonna expand your signature to make them unique, so that all the important data structure have their own different signatures. So skip all those details. So if we have an implementation, our implementation actually is on QMU. It's actually it's not on QMU. We just use QMU to collect your memory snapshot, right? Then here's the sum result. Right? The first column shows the important data structure that we're interested in. For example, the first one corresponds to the task struct. The second one is the threads, which tell you how many threads are present in your current memory. Right? And we actually use QMU, which is a virtual machine, to identify all the true instances. And then the SIGGRAPH, the 2 columns correspond to SIGGRAPH, actually our result. The value invariant correspond to the state of R, which use the magic number to scan the memory. You can see that, for our case, we have pretty much 0% false positive, right? And in comparison, the state of R, in some cases, they have almost all of the reported cases are false positive. That's because the magic number are just too general. They're not unique enough. They identify a lot of bogus instances. Look at the false negative, we never miss important information. And then the competitor actually missed some of them. We also miss a little bit of information which I will skip. Now this one we actually evaluate our technique on the rootkit detection. These are a number of existing rootkits. And then we simply just identify the task structure or the module, essentially, which is similar to task structure. It's also a linked list, which will link all the active module together. When you use the PS command, this is the number of objects that are reported by the command. Right? For example, you run PS. This is the list of processes that are reported by PS. For example, here you show 23. You see 23 processes listed by PS. But when you run our scanner, we were able to find one more what is that additional one? That's a rootkit process, right? So that tells us, okay, our technique is able to detect the rootkit processes, even though they hit themselves by dislink them from the linked list. Right? Now, SIGGRAPH essentially, it still has some limitation. The problem essentially lies in this. What if I have a data structure? A data structure has some field, for example, like integer field, okay? And then you scan the memory, you find the memory have a value of 0. Should I consider that 0 as an integer, or should I consider that 0 as a pointer? Well, pointer may also have a value of 0, right? It may well be a character, right? It's the end of a string. So you cannot say for sure this is a integer or not, right? So what we are saying here is that, fundamentally this is a probabilistic inference problem. You can never say for sure. The memory forensics, you cannot say for sure. All you can say is that, this is probably, or this is likely a integer, this is likely a pointer, right? So dim sum, essentially we extend our technique on SIGGRAPH. Now we make it a probabilistic inference technique. Now instead of saying, okay, this gotta be an integer, and then rely on the fact this is an integer, then now we're gonna say that, okay, this value, we have 30% of chance is integer, 30% of chance of it is a pointer, 30% of chance essentially is a character. Then we aggregate all these probabilities along the graphical signature, and on the top we're gonna compute a confidence, and this confidence will tell us, okay, with all this guess you have made, all right, then we say that, okay, now I have 50% of confidence this one is a task structure. Of course, 50% is not good enough. Usually what we get is 90%. This is a task list. Right? So basically what we're saying is that we aggregate the information from all the leaves, okay? Aggregate all your belief on the leaf nodes, and then we get a probability on the top. Right? So we'll skip that. I will get into the exciting discrete. Okay, we'll skip all that. This is you know that this is a very famous probabilistic inference graph, right? Belief propagation, if you ever work on this. So discrete. All right, the basic idea of discrete is that, the state of R before discrete, those state of R memory forensic technique, we report something like this, okay? They're going to tell you, this region of your memory actually corresponds to a JPEG file. And that piece of memory corresponds to a PDF file. But does it help the law enforcement? It doesn't, right? Because you want to see the content of the figure. And you want to see the content of a PDF file, right? Because they simply tell you, okay, this region, this bits and bytes actually is a JPEG file. Does it help? Right? I want to see the content, what's going on in that figure. Right? So basically, discrete solve the problem of content rendering of your forensic evidence. Render your evidence so that the law enforcement will have intuitive understanding of that evidence, instead of having those hackers will point you, okay, this is that figure on the screen actually correspond to a PDF. You have all those links going on. It doesn't help law enforcement, right? So here I will just give you the brief idea, and then I will go to a demo. Right? So how do we render the stuff in the memory? Okay. So remember that the information in your memory actually is different from the artifact on the disk. For example, when you load a JPEG file from the disk and then you put it into the memory, the internal data structure actually completely different. Not completely different. It will be different from your image on the disk, right? If you simply just run a JPEG viewer on that piece of memory, you're not going to get anything because it's just different from your hard disk representation. So the key observation here is that the application that bring the JPEG image from the disk to the memory usually has the logic to render that image, right? So otherwise, why would you bring a JPEG file into the memory? So for example, and you have an application which will read Acrobat reader, read a PDF file from the disk, right? You also have the logic that will render the PDF to the screen, right? So what we're going to say here is that you have this technique like Bistro, we can extract a piece of code from your application. Why don't we just extract that logic, right? That render the evidence from the application, and then we run it independently as a memory render, right? So that's the key idea. So skip all this technical details. So we go right to the demo. So yeah, this is a PDF file, and then this PDF file is kind of like a evidence of some crime, right? And then this crime actually was committed by Brendan, and then Brendan has tried to hide his crime by modifying this PDF file. Right now, it changed to William Gates. Basically try to blame William Gates for that. Now at the moment, the law enforcement come. They freeze the computer, and then they will try to get help from us. Right? But since Brendan hasn't got a chance to save the file to disk, right? So all you have is just the memory on the computer. And now we try to scan the computer, try to identify what Brendan was doing when the crime scene, when the crime occurred, right? So this is actually the detail of the technique. I will skip that because I haven't explained how the technique works. We go right to the 340, I think it should be. So this is how you run discrete. We actually get a scanner, and then you're providing the suspect's memory. You also have to provide the original binary, which is the one that added, the Brendan was using to edit the PDF. Okay, and you have to provide some random input to the editor. Now it starts scanning. So at the end, I have to skip a lot of the demo because I haven't explained the detail of our technique. Right. So essentially, at the end, we generate something like this. We scan the entire memory. As long as we identify instance of a PDF, if we're gonna render a PDF, that will become a file that's visible by any other Acrobat, any other PDF reader. Okay. If you save those rendered evidences into the disk, that's why you find that okay, we have one evidence identified by our scanner and renderer. So this is actually a legitimate PDF file. When you open that PDF file, you will see that there's a William Gates there. That's exactly what happened when the law enforcement came, right? And remember that file was never saved to the disk. It only occurred in your memory, right? Brendan was modifying the PDF file, and he wasn't able to save it to the disk. And law enforcement came, and then all we have is just the memory. Okay, he was able to close the application, but the memory is still there. All right. Any questions about the scenario? So I think we have some more exciting work going on. Basically, so what we can do lately is that we are able to reverse engineer, or you are able to identify your preview images from your Android phone. Okay, for example, you have your Android phone, you turn on the camera, and then you preview the images, but you're not taking the pictures, right? So then some important things happen, and you forgot to press forgot to take the picture, right? But using our technique, we can still extract those preview images that you have kind of viewed, right? And then that will include the important thing that you actually missed, right? And we believe that memory forensics has a lot of opportunities in mobile applications. And that's what we are heading these days. Any questions? Yes?
When you mean by that you are doing memory scanning, so do you also consider the virtual memory as well, or just the physical RAM?
Oh, it doesn't matter. I think we do both. Okay. Essentially, the difference between the physical RAM and the virtual memory is essentially whether you have the mapping information or not. Right? So our technique doesn't assume the presence of the mapping information. In other words, we actually scan your physical memory. Okay. That would be, I would say, it's a superset of virtual memory. Okay. Other question? Okay, this image actually summarizes what we can extract using discrete. You can see that we render a lot of things, including map, JPEG images, some log information, PDF file. Right? So all this, as long as the application have the logic to render such information, we are able to extract it and render the important information to your screen, the law enforcement screen. Right? I have a few more minutes, and then I will try to quickly go through our third topic, which is reverse engineering. All right. So what we do here is that the scenario like this: you download a piece of code from internet, and then it looks like it's doing something useful for you, but there may be a hidden behavior. Right. So how do you identify such a hidden behavior? If you use a disassembler, usually it doesn't give you anything because the binary may be packed, may be obfuscated. Right. So you run IDA, many times that you find that IDA will give you something completely not visible or completely not reasonable. And how do we reverse engineer the possible behavior of your binary? Okay, then have all the hidden behavior. Now see here, this is a technique that we recently developed, so-called X-force. So the idea is that we're going to force your binary to execute. So what does it mean? So when you download a piece of Trojan application, right? This malicious payload usually is protected by some kind of conditions. You wouldn't trigger the malicious payload unless the right condition is met. Right? So either today is some special day, or either the system is the right system I want to attack. Otherwise, I will not execute my malicious payload. Right? So, but you cannot hide from our technique because our technique is so-called X-force. We force it to execute. So what's the observation? So what is this kind of protection? This kind of protection, when you look down to the binary level, they're usually just a conditional jump, isn't it? Right? You compare with some condition, and then you jump based on the comparison result. What if you change your comparison result? Even though you say that, okay, today is December 10th. No, our engine will say that today is not. We just negate your branch outcome. Then you are forced to execute, right? Of course, this is the basic idea. There are a lot of challenges. Now, you go ahead with your debugger and you try to change the branch outcome, which I believe you can do. What will happen? Will crash on you probably in 10 more instructions, right? Now, our contribution is really to have a so-called the crash-free execution model, right? So basically, we force it to execute along a path, and then we also prevent you from crashing. How do we achieve that? So how does a program crash? You tell me, how does a program crash?
Legal memory access.
Exactly, illegal pointers, right? So what we can do here is that we detect the presence of illegal pointers, then we allocate a piece of memory and then give it to the pointer, and we just go ahead. Oh, don't laugh, it actually works. Right? and we got it published and we got it released to DARPA, right? So nothing wrong with that, it works. And then we are able to expose a lot of malicious behavior. One of the things that I can, skip all this technical details. I will show you a little bit of the demo, which is probably the last page of the demo. So here we use our technique to analyze APT malware. So you all know APT malware, right? The ones that persistent attacks, right? They are kind of very stealthy, and because they hide themselves, they try to perform the attack very slowly and gradually. How come? Right. So here we try to use X-Force on a APT malware called DG003, and this one is a multi-stage conditional guarded and environment-specific malware. If the condition is not right, it's not going to work. Okay, it's not going to turn on any of the malicious payload. It will just hide itself. It just look completely normal, right? And then basically we just skip right to the end and show you what we are able to do. Right. This image actually show you what we can do. Now this we are not the first one to analyze this malware. All right, we got it from I believe Sense Institute, and they actually have a 30 pages report about this malware, and they report part of behavior. And then we run our tool on this part of behavior, and we found all this additional behavior that show on the left top corner of the image. Right? So they correspond to the highlighted places in the control flow graph. So that the original report actually missed the behavior of delete a specific file, and then the malware update, and the most malicious behavior of this malware is delete all file on hard disk, and that's missed by the original report. And that's because this payload can only be triggered under very specific conditions, and our techniques are able to force the malware to execute along that condition, right? And actually, when we run this malware, and suddenly, we run it, and then because the technique is currently slow, we run the script, and then the student actually went to sleep. And the other day found out his entire hard disk is gone. I couldn't figure out what's wrong, and then later on, by some manual inspection, we found that we probably should be careful about this malware. You just delete the whole file on your hard disk. Okay. That's that. And currently, what we're doing is that we try to provide X-Force as a web service. Okay. So we're providing a web interface, and then you turn in your executable, and then you run it on our cluster, and then we're going to return you something like this, some graph like this. Okay, we're going to tell you all the behavior of your program. Okay, so we are still constructing the website. Currently, we can handle simple malwares, and hopefully, in the next few months, we should get the website up running for probably much larger binaries. Probably at that time you're gonna.
How are you gonna do it for analyzing the malware if it's simple or not?
We'll look at the size. I mean, right now it's pretty much by the size. Right? So a few hundred KB should be fine. So it's large. More than that probably will take a lot of time to execute all the path. Right? So I think I heard that as I should present for 15 minutes, right? So if you have any questions, let me know. Yes?
So when you're scanning memory, do you deal with pages that have been swapped out to the hard disk? Can you find those?
Yes, there's no difference for us. We actually can scan the swap file. Right.
Does your code deal with functions that have to do with as data obfuscated or encoded?
Which technique you're talking about?
Obfuscating data, like sometimes when you use IDAPRO to open a malware,
right.
It's saved as data, not an actual function.
So you're talking about pack malware, basically.
Yeah.
Yes, we do. I mean, X-Force actually handle pack malware, and this DG003 actually is packed. I mean, part of our demo which I skip. When you open it with the IDA, you can only see 3 functions. Okay, and then with our technique, we see hundreds of functions. Right. So because we force it to execute, force it to unpack itself. So you see the entire picture of the malware. Okay. Any other questions? Okay, thank you.